A hash table is something you call a dictionary in Python, map in Go, hash map in Redis, and simply hash in Ruby. It's an efficient key-value data structure, so it associates values with specific keys. From the outside, a hash map usually looks like this. It has a put method, which stores a value for the given key, a remove method, which removes the value associated with the provided key, and a get method, which retrieves the value associated with the key. Today let's look at how to implement these methods and set up the underlying structure of a hash table in Java. But first, time for a bit of theory. One of the things we need is an array, a block of memory with say 6 places. We'll call this array table. We know how to address the cells in this table because we know that they are numbered from 0 to 5. So if we want to store a value to the cell 3, we know how to do that. Now, numbers is one thing, but we need a way of associating an arbitrary key with a particular cell. How do we do that? Well, we can take this arbitrary key and send it through a hashing function, which always produces the same hash for the same input. We learned from implementing the blockchain that a hash is nothing more than a large number. This number is obviously too large to fit into our table, so we divide the hash with the length of our table and take the remainder. In other words, we calculate hash modulo table length. We have our number, so we put the value of the key to the associated cell. To retrieve the value of the key, we do the same thing, we just read from the target cell instead of writing to it. We can write to our table over and over again, but sooner or later we're gonna come across a case where the cell with the calculated number is already occupied. This is called a hash collision. There are different ways of handling it. The most common ones are open addressing, of which the simplest version is called linear probing. In this implementation we just occupy the next free cell, and for reading we do the same thing, just continue looking through our table until we find the key we're looking for. The thing that slightly complicates this is that when we delete a value from our table, we must set a tombstone in its place, otherwise we wouldn't check the cells after this one. The other common way of handling collision comes in form of a chained hash table. Here, instead of storing values directly in our table, we store the pointer to the head of a linked list in each cell. Conceptually, this is like having a list of all values with the same hash in one cell, and we'll call these lists buckets. In this case, when we store a value and the hash collision occurs, we simply append the value to the end of our bucket. When we want to remove the value, we simply delete it from the bucket and basically short-circuit the linked list. When we're reading the value of the key, we calculate its hash and then loop over all the records of our bucket until we find the one we're looking for. Chained hash table is in my opinion easier to understand, so we'll implement this one. It comes with a downside that it's probably a bit slower though. As you were probably able to tell, for this to work we need to store keys alongside the values as well. Another thing we'll need to take care about is resizing the table. We'll define a load factor which is say 75%, and then when the map will be 70% full, we'll double the length of our table and recalculate the hashes of all our keys. Now let's start looking at the code already. The code for this example is inspired by 2 blog posts I found by googling. I'll put a link to both of them in the description. Now let's scroll through the file. We have the main function with the test case, which we'll look at the end, and then we have the definition of the hash table class itself, and inside its body we have the put, get, and the remove methods alongside some other helper functions. Let's scroll back up to the start of our hash table class. If we look through the slightly repulsive Java syntax, we can see that the class has 4 fields which all have familiar names. Capacity is the current length of our table, load factor defines the percentage which determines when we'll resize the table, size is the number of currently stored keys, and table is an array of linked lists, so in our words, a table of buckets. Now, even though implementing a linked list isn't hard at all, my implementation cluttered the view of the other hash table concepts too much for my taste, so I decided to use the linked list from the standard library. We're also using generic arguments for both key and value, which means we can use any type of variable for both of them. Next we have the constructors, which just set up the initial state of fields, and below them is a definition of another private class called node. This is nothing more than a key-value pair we'll store in the buckets. Then for the most important helper function of our example, hash, which calculates the hash of a given key. Now, the choice of a hashing function is very important. It must be fast and it must have enough entropy to spread the keys evenly. We don't want all keys to end up in the same bucket. Luckily for us, types in Java have a built-in method for calculating a hash code. so we'll just stick to it. And now for the interesting part, operations. The obvious place to start is the put operation. You can see that we have a public method which takes a key and value as arguments. But let's step back a bit and look at the helper function insert first. The reason this is a helper function is because it's needed for resizing as well. Otherwise it would be cleaner to put this code in the put method directly. The insert function takes a table argument, the index of a cell in that table, and a key value pair to store at that cell. So the first thing we do is we check if a linked list already exists at the target cell in the table. If it does, fine. If it doesn't, we create a new one. Then we loop over all records of this linked list and check if a record with the key we want to store already exists. If it does, we update its value. If it doesn't, we put a new node to the end of the bucket. Because of the insert helper, put method looks really simple. We just increment the size counter and we resize the table if the new size is greater than the load factor allows. Other than that, we just call the insert function with our internal table field, calculate the index using a hashing function, and pass in a new key value node. You might be wondering, what does resize actually do? It's defined near the bottom of the file, so let's jump there. When we were talking about theory, I said that when resizing, we double the size of our table and then recalculate all hashes of our keys. And that's exactly what we are doing here. We create a new capacity variable, which is 2 times the current one, and we also use it to create a new array of linked list, or table of buckets. Then we loop over the current table and over all its buckets, and we recalculate the index of each key and insert it into the new table. Lastly, we just assign the new table and new capacity variables to their related fields, which overrides the old values in the process. Okay, if we scroll back up, right below the put method is get, which is probably the simplest one. It receives a key as an argument, which we pass through the hashing function to find the correct bucket in our table. If the bucket exists, we loop over it until we find a record with the searched key and return its value. In the cases where either the bucket doesn't exist or there is no record with the searched key in it, we simply return null. Remove method also receives just the key as the argument. We use the same technique to find its bucket as with get. If the bucket exists, we loop over all its records, and if there is a record with the same key, we remove it from the bucket and decrement the size counter. Nice, we're basically done. Now let's take our hash table for a spin. Let me just show you one method which we skipped first. It's at the bottom of the file and it's used for pretty printing the table. It looks way more complicated than it actually is. Anyways, at the top of the file we have the main function, which we'll use for a simple test case. I created wrapper functions over put and remove methods, which just log the intention and print out the state of the map after the operation. The actual main function then creates a new instance of a string key integer value table, and just to test the resizing, we use the initial capacity of just 2. Then we fill the map with a few values, update a key, remove a key, and finally we read a couple of values from the table. Running this file on the command line is as simple as typing this. Let's look at what our program printed out. We started with an empty table with the capacity of 2. Then we inserted a key apple with value 1, which was assigned to index 0. We then also inserted a banana, and in the process our table was resized to capacity 4. Banana got its place and apple was moved. When inserting orange, it ended up with the same result of hashing as apple, so it was added to the end of the same bucket. And finally, inserting grapes resized the table again. This also moved apple and orange to separate buckets. Next operation tried inserting orange with value 8, but because the key orange already exists, it just updated its value. Then we removed apple from our list, which, well, did exactly that. And finally, we read values of banana and orange. And if you look at the last printed state of the table, the values are correct. Phew! We finally reached the end of this video. It was pretty long, but I hope you still had at least a bit of fun. Anyways, thanks for watching the video until the end, and I hope to see you again. Bye!